Okay, good morning everyone. Last week I already showed you the part one of the new lecture, which is power factor and measurement of distortion. So today I'm going to give you a tutorial on power factor. Let's start with this problem. You can see here we have the voltage source as a sign as a AC, and we have several elements including resistors and several resistors and several inductors. So here the question is to ask you to find power factor. Actually the circuit here represents a motor. That's why here the question is to ask the power factor. What power factor is the motor operating? Let me use full screen to duplicate. Okay, in order to solve this problem, you need to go through the right steps. So I'm showing here 5 steps in order to solve this problem. I'm not giving very detailed, and I will just explain the step what you need to calculate. So it's better to understand the whole picture, the big picture, rather than the detail, minute detail on everything. So step 1, you need to find equivalent impedance. So impedance, for example, impedance for resistor here, let's call it impedance 1, it's just R itself. Impedance for inductor here, let's call it Z2 equal to J L S omega, like this. So it defined in a complex plan. So yes, impedance is complex number for each element, but for resistor it is a real number. So you just use combination of series connection and parallel connection. Finally you can find the equivalent impedance of the whole circuit. So you can combine in terms of real number and complex number like this. After then you can draw step 2, you draw right triangle in complex plane. One edge of the right triangle is X and the other one is Y on the imaginary axis. So you can have angle phi here. Next you find the amplitude, amplitude of the equivalent impedance Z, which is actually just square root of this edge square plus this edge square, because the absolute value of Z equivalent is this hypotenuse. Okay. And then the step 4, you find steady state current. You will see how you get that in the next page. Then step 5, you can easily find power factor using the formula you learned last week. So here actually to find the equivalent, the sub-equivalent of impedance for Z4, Z5 and Z6, because they all connect in series, you just add them up, okay, in terms of a complex number. And then this term is connect in parallel with this, then you use this formulation, equivalent conductance equal to sum of all conductance in the parallel branch. Okay, or conductance just inverse of impedance. So finally you can find sub-equivalent of inductance on this part. Okay, and then this equivalent of impedance on this part just series with the Z2 and Z1, and then you just add them up, and finally you combine the real part and imaginary part accordingly. So then you can go to step 2. draw the right triangle, and you get the real number x here and imaginary number y here. Then you can easily find the amplitude of Z equivalent. Okay. Then step 4, find steady state current. The steady state current actually just amplitude time cosine, because the source here is cosine, right? And cosine omega t from the source. But for the current, of course, it has phase shift. Okay, this one is voltage, then current has phase shift because we have a storage element here. The amplitude can be defined by just amplitude of voltage divided by the amplitude of impedance. Okay, and then the phase shift actually is just a term of, I should write down here, phi is just a term of y over 8, right? Because you look at this right triangle. Okay, yeah, already defined here actually. And once you got current steady state, actually the formulation, the original formulation of power factor is equal to real power over apparent power. Apparent power is V root mean square times I root mean square. And you can find root mean square easily once you already have the waveform of current and voltage. This is the waveform of voltage. The root mean square is just the amplitude divided by square root of 2. Same for I, the root mean square of I is just the amplitude divided by square root of 2. But anyway, in this case, there's no bridge. I mean, there's no switch element. Then you can have power factor just like this, because P is just V root mean square, root mean square, I root mean square times cosine phi, and then you divide it by this, right? Then you cancel with this, and you just have cosine phi. So look at here. Actually, the edge of the real part represent the real power. This one represents real power, and this part represents reactive power. That's why you can easily find power factor, which is the ratio of this and this. No, cosine. Yeah, cosine. So cosine is the ratio of this edge over hypotenuse. Okay. So yeah, it's actually easy if you know the steps very well. Okay.
Why do we need to find a current at steady state? Why don't we find the co-phi directly through the graph?
Yeah, that's a good question. Yeah, actually, I would say if, in some case, if you it depends if you realize that, okay, this system there's no any kind of switch, there's no distortion, there's no, we call it the distortion factor. Then you don't need step 4. You can go directly to this part, the problem. But some case you must find this one first before you apply this formulation. Okay, you need to find I root mean square and V root mean square. Yeah, but for this particular problem, you can skip this one. All right, let's go to the second example. Yeah, now you have switch. It's not like the previous one, right? So in this problem, actually, you have current source here, and then you have half bridge of diode connect in this way, and at the load you have one resistor and capacitor in parallel. So here assumption is given that the capacitor is large enough. This one, it's large enough to maintain the voltage here to be constant as VD. Okay, so when writing a lowercase VD like this, it means instantaneous. So actually instantaneous value here, it's almost a constant. This is what it means, right? So then when you talk about voltage at the load, you just say it constant capital VD. Okay, capital VD, this one. Okay? And now here the question is to ask you to determine the power factor seen by the current source. So you find power factor seen from here. So you got a step in order to find power factor. You need to find real power and apparent power. How to find apparent power? First let's say apparent power, which is V root mean square and I root mean square. Which means first you need to define waveform of this one. Okay? And then you find root mean square. Also current, you need to find its waveform. Maybe it's like this. And then you find its root mean square. So you got apparent power. After then you need to find real power. This one. Real power can be found from the load part from here. And or actually you can find a real power seen from the source, so you just work on this part. Real power actually is just from the average value. You got the formulation 1 of t 0 to period, and then the p of t dt. This is the original formulation of average power or real power. Okay. I think I give the detailed step here. Yeah. So step 1, try to draw the waveform of current ID. Current ID, which means the current go through through D1. Okay. But by the way, let me explain what happened in this circuit first, so that you understand why I want you to you need to find ID. So here you have current, so which means current flow from here has to be this form, this waveform. So when the current is positive, of course the diode can turn on, this one turn off, because current cannot flow opposite direction, right? And then the current goes through 2 branches, one storage element capacitor, and then the other one goes through the load R. And when current is negative, which means flowing this way, so when it flows this way, it cannot go this way. Why? Because this one block cannot go this way, or cannot go this way. This one already blocked, so it can only go this way, like this, when current I is negative. Okay. So when the current flow this way, there's no power factor, because there's no power used at the load, right? When it's flow this way, so only current flow this way is going to be used, right? Yeah. So it's important just to find the waveform ID here. Then step 2, do the analysis to obtain waveform of voltage VD. Here, voltage VD. Okay. And step 3, do the analysis to obtain waveform of the source. After you got the waveform of VD here, and then you do analysis to get waveform of the V at the source here. Okay. Alright. After that, compute V root mean square and I root mean square of the source. The source. Okay, because you already know the waveform of the source, I mean voltage of the source and current of the source, you can easily compute V root mean square and I root mean square. Okay, so you can calculate the apparent power. Step 5, compute the real power. Yeah. So actually the real power would be the power that goes through the resistor. Okay, so you can easily compute it from the power from the resistor. You don't need to use this formulation actually, but you can if you want to. Yeah, so here the detail, how can I get this waveform? Yeah, like I mentioned earlier, for the ID, it flows through ID when sine wave is positive, from when the source sine is positive. Then when sine wave is negative, ID is 0, like this, and repeat. And then once we know ID, then we do analysis to find the current, the average value of current IR goes through the load R. How can we do that? First, we use Kirchhoff current law. This current equal to this current plus this current, right? And then we apply average value. And you remember periodic steady state, average value of the current go through in and out of capacitor is 0, right? In and out in capacitor. So the average value is 0. Then we can have average value of current across this diode is just same as average value across this resistor. Then we can compute voltage here, average voltage VD, which is just current times resistance. And this average voltage here from assumption is that average voltage is capital VD, because we have a storage element here, so VD itself is just approximately equal to this capital VD. And then you can make analysis to find Vs. So here is Vs. Voltage Vs here, when D2 is off, this terminal is just parallel to this and parallel to this, right? D2 off and D1 on, right? So Vs is just parallel to capacitor and parallel to resistor, which means voltage of the source here is just the same as voltage at the load. That's why VD here is just like this. Okay. And when D2 is on, D1 is off. So here it just is short here. Short from here to here, which means Vs during this time is 0. So Vs is 0 here. And then it repeats. Okay. What I'm trying to okay. So this waveform is just VD 0 VD, right? If you say VD is constant, VD times this term, it becomes just square like this, right? Yeah. Yeah, this term is just 0 and 1, right? When this part is positive, sign of positive number is 1, 1 plus 1, 2, 2 divided by 2, 1. When sign value here is negative, then the sign function of negative number is minus 1, minus 1 plus 1, 0. So this term just 1 and 0, 1 and 0, okay? And then you can compute, step 4, you can compute root mean square of voltage and current. So you can calculate apparent power, apparent power S. Because I is just sine wave, then root mean square is just amplitude divided by square root of 2. And for V root mean square of the source, because you already have the waveform is just square, right? Like pulse, right? Then you can integrate over a period, but the period is 2 pi, but it has value only from 0 to pi. This part is just 0. So finally you can compute it, and it's equal to, where it is, equal to just Vd over square root of 2. Then apparent power can be computed. Step 5, compute real power. So the real power is, actually I use the original formulation finally. So power equal to power seen from the source, right? So power equal to current of the source times voltage of the source. So you get this, and then you can simplify, not really simplify, but when you apply the integral, the finite integral over a period, the period is 2 pi, but because Vd exists only from 0 to pi, then you only need to integral from 0 to pi. Then finally you get this value. And then real power is actually this term. Then power factor is the ratio between real power and apparent power, and finally you get this, just 33.66%. A little bit fast, but I think it has very detail in here, so you can read it later. But anyway, you have questions, please, you can ask me now. Any question? Udon?
Yes. If I want to increase the power factor, I should increase the capacitance, right?
No. You please distinguish between system with inductive load. If you have system with high inductive load, then you use capacitor to compensate it. But this power factor actually happen due to the waveform distortion. You can see the waveform of the current source is sine wave, okay? Purely sine wave. But the current of Vs is square. So it distorts from the nice sine wave to just square like this. So power factor due to the bridge itself, due to the bridge of the diode. And here there's no power factor due to displacement. So inductive load from like the previous example, power factor is due to the displacement. Okay? This capacitor actually is just to maintain the voltage at the load. It does not cause any reactive power. Yeah. But of course, why we need to use light capacitor? We use it to be light because we want this one as straight as possible, because we want load to have direct current, DC current, and DC voltage. Okay, that's why we need to use light capacitor. Any more question? Yeah, it's good you ask question like this. So there's so many ideas behind this. So. All right, if no more question, then I can go to the next part, but I will stop this one first.